Hello, everybody, and welcome to the second session of the second day of PLDI. I hope you're having a good time, and I hope you had a good lunch. So this session is, so it's labeled automata theory, although I would sort of call it a mix of automata theory, logic, type theory. And our first talk in this session is by Ondřej Lengál, and he's going to talk about how to handle position constraints in modern string solving. Ondřej.
Okay, thank you for the introduction. Thank you everybody for coming to this talk. This is a collaboration with people from Brno and also Yu-Fang Chen from Academia Sinica in Taiwan. So what are we talking about here are string constraints. String constraints are constraints in this SMT theory of strings. So you have a first order logic that is treating the string as some basic data type. And the constraints look similarly to what is written in this slide. So you can have some equations, you can have some disequalities, these can be of some variables, or it can be of concatenations of variables, potentially with some constants inside. You can have some regular constraints, so you want to say that some variable belongs to some regular language. You can have length constraints, so you can say the length of some concatenation of variables is 3 times smaller than something else. Or you can have also some more expressive constraints, such as not contains something. Why is this important? It's important because if you want to reason about programs that are dealing with strings, and these are currently many programs because string is the basic data type of a lot of scripting programming languages, you can use this logic to express things like some SQL injection attacks in PHP or things like that. Or it can also be used in analysis of some access policies, such as they use in AWS or in Rego. Recently, it has started to be widely implemented in solvers, both in some deduction-based solvers, such as Z3 or CVC5, as you probably all know. And also, there is a bunch of so-called automata-based solvers like Norn, Trauslov, Ostrich, and Z3 Noodler. Z3 Noodler is a solver that I'm a member of the team developing it, and this is a very interesting project because we started something like 2 years ago from nothing. We started building on top of Z3, removing the basic string solving algorithm, exchanging it for automata-based solving algorithm, and we got to the place that in last year in SMT.com we won the string category in all of the possible scoring criteria. In this talk, I will be talking about just some fragment of string constraints. I will not be talking about word equations. These are solved by some other works. I will be talking about constraints which are, in particular, regular constraints. So we consider that the string variables are all have some regular language that they belong to. And then we will be talking about disequalities, length constraints, symbol is at a position or symbol is not at a position, not prefix, not suffix, and not contains. These things will be called position constraints. Why will they be called position constraints? The reason is that they are satisfied by an existence of an interesting position somewhere. So if you look at this example of some disequality, xaz is not equal to ux, this is satisfied if there is some natural number I such that if I look at the index I in this concatenation, it is not equal to this index to the position at the index in the other concatenation. So if you look at it in this picture, there is some kind of mismatch between the occurrence of at some position in Z and some position in U. For not suffixof, I can also express this as some kind of existence of an interesting position, in this case from the back of the strings. And if I look at not contains, this is more complicated. I will be talking about why it's complicated later. Now we have some kind of like, if there is some not contains, I'm saying that for all offsets, there is some mismatch somewhere. So I have something like universal existentially quantified formula. Our approach is how to solve these constraints is that we will construct a special kind of an automaton called a tag automaton. This is nothing fancy, it's just a finite automaton that is extended in some simple way. I will talk about it later. We will use some very nice theorem that you have all learned in the kindergarten, so-called Parikh's theorem. For this talk, we will use a very simplified version, which is saying that the number of occurrences of symbols in words in regular languages can be described by a linear integer arithmetic formula. So if you have regular language and you are only interested in the number of occurrences of symbols in the words which are generated by this language, then you can use a linear integer arithmetic formula to encode it. And then we will construct a Parikh formula which will be encoding these constraints into a linear integer arithmetic formula, and then we will solve it by the off-the-shelf linear integer arithmetic solver. So what are these tag automata that I will be talking about here today? So the tag automata are over some set of tags, which is just some set of some things. And it is an extension of finite automata, where the only difference is that on the edges of the automaton, there is not a single symbol, but there can be multiple symbols. So you can see it as you have a word, and at one position of the word, there are multiple overlapping symbols, and all of them are somehow active at the same time. So there is an example of some tag automaton. This looks very similar to a finite automaton, and we will be constructing this tag automata from finite automata just by taking the finite automata and putting there some special tags. In this case, we take two automaton for the language of a variable x, automaton for the language of variable y. We are connecting them together. By this dashed line, I'm expressing something like an epsilon transition, which is just encoded as a transition where the set of text is empty. And with this automaton, we will construct their Parikh formula. So as I said previously, we will construct a linear integer arithmetic formula over variables which are taken from the set of tags, and we get for every tag in the set of tags, we get a new variable which will be encoding the number of occurrences of the tag in the accepting run of the tag automaton. So assignments are corresponding to mapping of the numbers of tags to some natural numbers. And if we have some assignments, so it is a model if there is an accepting run in the automaton such that the image of this assignment or the assignment to this variable is the number of occurrences of a tag in a word which is accepted by the automaton. So for example, if I have this word AB, AC, AC, so it is in the language of the automaton. If it is in the language of the automaton, then this assignment, so if I assign number 4 to the number of occurrences of the tag SA, number 2 to the number of occurrences of the tag SB, and 2 to the number of occurrences SC, should be a model of the Parikh formula of the automaton. So let's start with the simplest constraints, which are length constraints. An example is here. So this is an example of a length constraint. These are regular constraints, so they are implicit in everything we are talking about. And we have some additional thing here, which is talking about the length of the strings. So what we do is we construct a tag automaton by connecting the automata for the variable x and y. So this is the automaton for the variable x. This is the automaton for the variable y. We transform it into tag automata. So we change the standard symbols into the set of tags, and for each standard symbol, we just put there this tag SA, for example, SB, and so on. And for every variable, in every transition in the automaton for the variable, we put there a tag LX. So if we count the number of occurrences of the tag LX in the automaton or in the formula or in the Parikh image of the formula, we will know what is the length of the length of the word which was generated here. So example of how to translate this constraint into the linear integer arithmetic constraint is that we take the Parikh formula of the automaton. I will not talk here about how to construct the Parikh formula. That is a thing which is somehow standard in the literature. And we put there additional constraint, which is saying that 2 times the number of occurrences of this tag needs to be equal to 3 times the number of occurrences of this tag plus 2. Okay, now let's come to a single simple disequality. So I will be talking about disequalities because they are the basic things we are dealing with here. And we have a simple disequality where we have a single string variable on each side of the disequality. So what will we do is that we will construct a tag automaton where the tags are now more complicated. So before we had these tags where we were having the symbols and we were having the lengths. Now we will also put there another tags, the position tags, px, py, and mismatch tags. And the idea of what we will do is that we will construct the tag automaton as in the case for the length constraints. If I come here, so we will construct this thing, and we will make several copies. We will make 3 copies that will encode how many mismatches we have seen. Because what we need to do is that we need to guess some position in X where there is a mismatch, and we need to guess a position in Y where there is a mismatch. So we need to have these 3 copies of the automata in order to be able to say whether there was a mismatch and at which position it was. So in the first copy, we know that there needs to be some mismatch in X, so we will pretty much start accepting something here. We will non-deterministically move to the second copy after guessing some mismatch in X. Here in the second copy, we need to make a transition from the automaton for X to the automaton for Y. And then at some point, we need to again make a non-deterministic transition to the third copy, where we know that we have already seen all the mismatches. And what we are doing along the way is that we are counting the number of P tags, the position tags. So you can see there are some PX tags in this part in the first copy. There are PY tags in the second copy. So we are counting the number of position tags, and we need to say that they are the same. So if I look at the final constructed automata, it needs to hold for the constraint to be satisfied that these numbers are the same, and also it needs to hold that there is really a mismatch. We need to check that the disequality really holds, so there is some position such that the symbols are not equal. So we need to check that the number of occurrences of this mismatch with some symbol A is different. It's less than 2, so that we cannot have like the mismatch cannot be over the same symbol. If we look at something more complicated, which is having a single disequality, which is not simple anymore. So in this case, we have on the both sides of the disequality, we have not a single variable anymore, but a concatenation of several variables. So this is a more complicated because now the mismatch can happen in several possible cases. So the first case is it can be between X and Y in this part. It can be between X and X. It can be between Y and X in this part, and also it can be between Y and Y. So now we need to extend our set of tags by having possible mismatch positions in X for the first mismatch and also in X for the second mismatch, and the same thing for Y. And we also need to extend the tags for the mismatches. And then the automaton looks a little bit more complicated. On the left side, these are 3 copies of the automaton for the variable X. In the right side, there are 3 copies of the automaton for Y. And we are also need to, the runs here pretty much, the accepting runs which go from the initial state, which is here, to the final state, which is here, need to see 2 mismatches. And they can be even in the same variable. So if I look at some particular position of the mismatch, let's say if it's in Y and it's in Y, the both mismatches are in Y, then there needs to be a run that does something in this part here, then jumps to Y, sees some mismatch here, sees some mismatch here, and so on. And this can be again encoded by a linear integer arithmetic formula that we put in conjunction to the Parikh formula. This is only for one case, but we can encode the other cases in a similar manner. For multiple disequalities, this is harder, so I will not go into details. The naive solution is combinatorial, so something bad, but it can be solved in a simpler way with a linear number of, with linearly increasing the size of the formula. If you want to see details, please go and check it in the paper. For other constraints, for not prefix, not suffix, and add constraints, this is a very similar technique, so you can just pretty much extend it straightforwardly. Not contains is more complicated. So in not contains, there is some implicit universal quantification that I talked about before. Because if you want to say that there is that some string is not contained in another string. You need to consider all possible offsets from the beginning. You could be tempted to solve it by some kind of universally quantified formula, but the problem here is that the universal quantification doesn't work. The problem is that after the universal quantification, there is some existential quantification over the transitions. So you would have the same number of occurrences of symbols, but they could be somewhere else. So you would be considering different words. So it doesn't work anymore. There is some example. If I have these two automata for U and V, then I can. If I have these possible models A, B, A, so this would not be a model because if I shift U1 to the right, then this is contained in V. But if I rearrange the symbols, then it is not contained as it is shown in this example. So we can only solve not contains for a restriction to something which is called flat regular constraint, which are constraints that disallow this kind of looping. So you can still have loops, but you cannot have multiple loops that come back into the same state in the automaton that is encoding the regular language. The details are in the paper. For the decidability and complexity, so if we take the basic regular language constraints and put their single disequality, this is decidable in polynomial time. If we take multiple disequalities or some combination of not prefix, not suffix of, this is NP complete. If we put there not contains over flat regular constraint, we get to non-deterministic exponential time. This is because we start having universally quantified linear integer arithmetic formula. And if we start with, if we also put there word equations, which are chain-free, which is some very interesting fragment for which many things are decidable, we still get a decidable fragment where the decidability is in, it's in elementary, but it is not a lower bound. For experimental evaluation, we try to compare with the state of the art, which is CVC5, Z3, and ostrich on benchmarks from symbolic execution and of some handcrafted formulae. The results are, so we were mainly trying to improve over the original performance of Z3 Noodler, which if you look at the last column, it helped a lot. These formulae were not cherry-picked, so there are most of the formulae are easy to solve. So it seems like we might have improved by solving like maybe 1% more of the benchmarks than previously, but this is from all formulae. Many of them are very simple. What is interesting is comparison with the state of the art, which is Z3 and CVC5, and this shows that our approach is orthogonal, so it is a very good match for a portfolio solver, and it can be beneficial to use this in some kind of application where you can have to have portfolio. Okay, so to conclude, I was showing this way how to deal with regular constraint by translation into tag automaton and linear integer arithmetic solver. It is efficient in practice, so that's nice. And in future, we want to solve the not contains, which is non-flat. We have some result now, which is under review for one not contains, and we want to go for some richer regular constraint that can have some back references or bounded repetition. Okay, thank you.
All right, do we have questions? Okay, so can you also tell us about what constraints you probably cannot solve using tag automaton?
Okay, so what we cannot do is word equations, but they are solved by something else. They are solved by some other techniques. There is if you take word equations which are unrestricted and length constraints, the decidability is not known. And what we don't consider yet are some things like transducers and stuff like that. So I think that many of them could be solved. In general, it is undecidable, but maybe there are some decidable fragments which might be.
So when you have length constraints on top of word equations, don't they translate to position constraints?
No. The thing is that because for word equations, if for a vertical equation to hold, that means that all of the positions need to be the same. While for the position constraints, there is just, it's enough that one position is different. So it's like,
so if I have upper bounds on lengths, then I can write it.
Yeah, if you have upper bound on length, that's all, yeah.
Okay. All right, let's thank Ondřej again.